Hello and welcome to this video. In this episode we will talk about computational secure encryption. We will discuss why this is actually necessary, we will consider the corresponding definitions, and we will also discuss how to construct a computationally secure private key encryption scheme, so stay tuned. In the first step, we're going to discuss the necessity for computationally secure encryption schemes. And we're doing this by looking back to the famous one-time pad encryption scheme. So how does the one-time pad encryption scheme work? Well, it works by taking a message of some length and XORing the message to a key of the same size. And the resulting ciphertext is then simply, as I just said, M XOR K. So the nice thing of the one-time pad is that it achieves information theoretic security, meaning that even an algorithm that runs for unbounded time, which means it can really run forever, will not be able to learn a single bit of information about the encrypted message. Amazing! So why don't we use this in general? Well, the answer is quite easy. First of all, it has two main drawbacks. The first one, as the name suggests, that you can only use each key one time. And since key management is a huge problem, right? I mean, for each message you would like to transmit, you would need to exchange a key before, and you don't know how to do it, so okay, there's no option. The second drawback is that the key actually must be as long as the message. And from a practical perspective, this is also awful. First of all, sometimes you just don't know how long the message will be, and generating these long keys is computationally difficult anyways. And in fact, one can show that this is a necessary requirement, which means whenever you want to achieve computationally secure encryption, the key must be as long as the message. Okay, since there's no way to improve this, we actually need to relax the security notions slightly. And this is where computational security comes into play. We're considering two relaxations. The first one is we're bounding the running time of the adversary. And the second one is that we will allow the adversary to win with a very tiny success probability. So we're going to take a closer look on each properties now. So let's start with computationally bounded algorithms. In general, we mean that the running time of the algorithm is bounded by a polynomial. And if we express this formally, this means that for any input x that we're giving the algorithm, there exists a polynomial such that the algorithm stops after p of x steps. And this makes sure there's always a certain running time. Well, since this is an algorithm, it means that the running time here is deterministic. So whenever we are running the algorithm on the same input, we will get the same output with exactly the same running time, because the algorithm performs exactly the same steps. However, in crypto, we are very often interested in so-called randomized algorithms. So these are algorithms that just toss some coins during its execution. So they make some random guesses. So there are two ways how we can formalize these. One is by saying, well, after each step of computation, the algorithm may toss a coin and decide whether it goes left or right. The second formalization is here shown in this slide, and it essentially says, well, we view the algorithm as an algorithm that gets two inputs. The first one is the actual input where it performs the computation on, and the second one is the random tape. And we distinguish these inputs with a semicolon, which means X is the actual input and R is the random tape. And one can show that this formalization is actually equivalent to the one that I just said before. Okay, so this is how we restrict the adversary, and I think it's pretty reasonable in practice, because we're not considering adversaries that run forever anyways, right? So we're interested, for example, in securing some medical data or some private information. And in many cases, this information is not to be protected forever. So in the next step, we would like to define what does it mean for an algorithm or an adversary to have a very tiny chance of winning. And we express this via so-called negligible functions. Intuitively, a negligible function actually is a function that goes towards zero very fast. And if we want to formalize this notion, we first need to formalize the notion of a security parameter. So the security parameter is essentially a parameter that is usually encoded as 1 towards lambda, and the lambda essentially says how many copies of the 1 we write next to each other. And we are doing this again to enforce polynomial running time. So why are we using the unary encoding? Well, if we use, for example, binary encoding, then this means that we can express the string n just with log n bits. And now if the algorithm gets as input a string of length n, it in fact means that it can run an exponential time. And therefore we're using the unary encoding to make sure the polynomial running time is fixed. So this brings us now to the notion of negligible functions, and we usually will define these negligible functions in terms of the security parameter. So here you can see that the definition is actually an asymptotic one, which means a function is negligible if all values that go after or bigger a certain threshold n, for all of these values the function f is smaller than 1 over p of n for all positive polynomials p of n. In other words, the function goes faster towards 0 than any inverse polynomial function. So let's take a look at 3 nice examples. The first one is the function 2 to the minus n. So what about this function? Yes, it is a negligible function. Why? Well, because it's obviously an exponential function that actually goes towards 0 exponentially fast. And because it's an exponential function, you will not be able to find any polynomial function that go faster towards 0. So let's take a look at the second example, the constant function. That's a tricky question. So you might want to pause the video at this point and think about it for a second. So the constant function is in fact tricky because we didn't define what the constant actually is. So if the constant, for example, is 2, then it is not a negligible function because it actually will never go towards 0. On the other hand, if the constant is 0, then it is a negligible function because it is already at 0. So what about the last example, 1 over p squared? So this function is not negligible because you can easily find a polynomial function that goes faster towards 0 than 1 over p squared, right? For example, 1 over p to the 4. So now you've seen 3 nice examples how to handle negligible functions that should help you to play around with this definition. In many security proofs, however, we also need to be able to compute with these functions, and they have very cool properties. So the first property that you can see here is that whenever you add 2 negligible functions, the result will also be negligible. And in fact, this we need very often for security proofs, because sometimes we are essentially considering different cases, and we are analyzing each case separately. And this proposition essentially tells us that if the adversary succeeds in each of these steps with negligible probability, then its overall success probability is also negligible. Another very useful bound, or another useful property, is the second one. It essentially says if we multiply a positive polynomial to a negligible function, then the result will remain negligible. And again, we use this very often in security proofs. In particular, sometimes we're asking the question, does the adversary gain any advantage by repeating a certain procedure many times? And in particular, polynomial many times. And the answer by applying this proposition is no. If its success probability at each step is negligible, then repeating the steps polynomial many times remains negligible, and therefore the adversary has no significant advantage in breaking the security. So one can show that both limitations of the one-time pad are in fact necessary. So we cannot construct an information theoretic secure encryption scheme where the key is smaller than the actual message. And therefore these relaxations are necessary. In the next step we are going to take a look on how to define security. So as you can see here, we are considering the standard setting that we are in, which means here we have Alice, and Alice and Bob would like to communicate securely. And this is expressed via this channel here. Unfortunately, right, there's always the bad guy, and that means the adversary A is sitting on the channel. In general, we assume that Alice and Bob shared this key K before, and we don't really care how they actually did it. Another intuitive security notion that we would like to achieve is that the adversary does not learn any information about the message that is exchanged towards this channel. Now, if we want to formalize this intuition, the obvious question is, how can we actually formalize this? So the first question that we have is essentially, who is choosing the message M? And how is M chosen? Well, one way that if we don't know how to answer these questions, of course, we could say, well, let's let the adversary choose this message. But if he chooses the message, then obviously the adversary knows what message is transferred, and therefore there's nothing to gain. Well, what we can do is we can essentially ask the adversary to output two messages, M0 and M1. And then we will choose one of the messages uniformly at random, which means the person who's sending the message, which will essentially be the challenger, flips a random bit B, and then we are transferring the ciphertext as the encryption using the K key and the message MB. And now the task for the adversary is essentially to tell whether the message M0 or M1 was encrypted, and he's essentially expressing this by outputting a bit B prime. So why is this a meaningful notion of security? Well, first of all, observe that a bit is the smallest information that we can express in any computer system, which means the smallest information that the adversary can learn is actually a bit. And ideally, we would like to express that the adversary is not even learning a single bit of information. So to make the game a little bit more accessible, you might think of M0 and M1 as actually being just one bit. Which means if M0 is 0 and M1 is 1, then distinguishing these two messages essentially means the adversary learned exactly one bit of information. In some cases, the encryption scheme might perform particularly bad for certain messages. It might be the case, right? So it works for almost all messages, but there are some weird messages where the encryption scheme doesn't perform very well. And therefore, if the adversary is allowed to choose the message, he can actually choose exactly these two worst-case messages. Which means, for example, if the adversary is particularly good in distinguishing the message 000000 and maybe 011001, these are just random examples that I made up, but suppose these are the messages where the adversary performs exceptionally well. Then what we are saying is the secure encryption scheme is the one where even if the adversary chooses these messages, he still cannot do better than guessing. And this brings us also to the security definition. So in fact, we're requiring that whatever the adversary does must be significantly better than the pure guessing strategy. And how can we express significantly better? Well, great that we just learned negligible functions and we're using them to express the success probability of the adversary in the following. In fact, we will say that the adversary wins the game if it is able to distinguish the messages with probability 1/2 plus something that is non-negligible. So let's take a closer look. So as you can see here we have the picture that we just created, right? We have Alice communicating with Bob in our attack scenario where the adversary is reading the messages. Furthermore, we said that the adversary is allowed to choose the messages M0 and M1, and for technical reasons, we will require that the messages have the same length. Now the message MB is transmitted, and the adversary has to predict which message was encrypted. And in fact, we will say that the adversary wins if it outputs B prime that equals to B. And on an intuitive level, we will say that the encryption scheme is secure if the best strategy for all efficient adversary is guessing. So what we are going to do now is we are transferring this intuitive description, which usually corresponds to the application we are interested in. So we are transforming this one into a formal game. So why do we need to transform it? Well, first of all, if we have this pictorial description here, it might not be clear what operation is executed at what point in time. And therefore we need a very compact representation that allows us to turn this intuition into a formal language where it's pretty clear what is happening when. So let's do this together. Well, first of all, I already prepared here the experiment. The experiment is the formal language that we will use to write down these games. It's essentially a random variable that we call privkey, and this name is arbitrary, but we're choosing it in such a way that we make sure it's essentially a unified notion for all further games that we get. We further distinguish the type of game by saying EAV for eavesdropper security. Eavesdropper security because we are assuming in our practical example here that the adversary is eavesdropping the message and has no further possibilities. Furthermore, we are binding the encryption scheme pi to this random variable as well as the adversary, and this is our security parameter. So how do we define it? Well, first of all, we are taking a look what is actually giving in these games here and at what point in time. And this we are essentially writing down. Well, first of all, we are taking the generation of the two messages, which means the first step of our game essentially is the generation of the two messages by the adversary who gets as input the security parameter. Right, so essentially this is the first step of the game that corresponds to this computation of the two messages by the adversary. So now the adversary here is essentially expecting to see an encryption of the message MB. Well, in order to compute this message, the next thing that we have to do is, of course, generate a key. Which means the next step of our game is essentially the key generation of the private key encryption scheme. Furthermore, the adversary, as we just discussed, is expecting to see the message MB. And therefore, we need to choose the bit B before. So we are now choosing the random bit B uniformly in this uniformly as follows. Now that we have the key and the bit B, we can essentially compute the ciphertext CB as the encryption using the key K and the message MB. And of course, as we said before, we're assuming that the messages have the same length. Now we're giving the adversary this challenge ciphertext CB, and it has to output its guess B prime. Note in general that we're assuming that this algorithm here is stateful, which means all information that the adversary generated here in the first place also is known to this adversary here. And of course, following the Kirchhoff principle essentially means that the adversary, of course, knows the entire encryption scheme. And now we are saying that the adversary wins if the guess was correct. And in this case, the game will actually return 1. So now that we generated this intuition together and also the game, we will obtain the following definition of security. As you can see here, we are actually now seeing the formal game that we just derived. And we will say that an encryption scheme pi consisting of the algorithms key generation, encryption, and decryption is secure against an eavesdropper if for all efficient adversaries A, there exists a negligible function such that the probability that the game outputs 1, which means the probability that the adversary wins the game, is actually bounded by 1/2 plus that negligible function. In other words, an encryption scheme is secure against an eavesdropper if the best strategy for the adversary to breaking the scheme is actually by guessing the bit. And even explaining this a little bit further, this actually implies that the adversary does not even learn a single bit of information by intercepting the ciphertext. So far we discussed the necessity for computationally secure encryption scheme, and we also derived the corresponding security notion for eavesdropper security. Now let's take a look on how to construct such a scheme. And we will start with the following motivation. Well, we start with the intuition that we're taking a look at the private key encryption scheme, which is essentially the one-time pad as you can see here. Remember that the one-time pad works by using a key K that has the same length of M, and we are simply XORing both elements together. So let's think about the properties that this actually has. First of all, the size is the same as we just discussed. And the second property that we have and require is that the key K is uniformly random. And this makes sure that essentially the ciphertext that we are obtaining by performing this computation is also uniformly random as well. So now what we would like to get is the following. We said before we would like to have a key that we can reuse, and in particular we would also like to have a key where the size of the key might be smaller than the message. And this brings us to the following formalization. Well, ideally we would like to follow this blueprint here, and this blueprint essentially tells us we want to encrypt the message with some random value r. How do we compute this random value r? Well, we are deriving it by running some algorithm G. So G will be a so-called pseudo-random generator, and what it does, it takes as input a small value key, a small value k, and it expands this value k. Why do we do it? Because this corresponds to our requirement, right? So we wanted to make sure that the key does not need to be as long as the message. And therefore, we are exactly defining an algorithm that essentially takes as input this key and expands it such that the output of the computation is as long as the message. Okay, so this essentially gave us the first property, namely that we can start with a small value and we get something that is longer. Now we need the second property. The second property to show security was that k is uniformly random. So we need to obtain something very similar. Well, we won't be able to derive something that has a uniform distribution, because then we would be able to get information theoretic security, which we know is not possible. Instead, what we can achieve is that the output essentially looks like being random. In other words, we are saying that the output of g of k is indistinguishable from a random string r. And this brings us to the definition of pseudorandom number generator. So what is a pseudorandom number generator? Well, a PAG for short is exactly the abstract description of the properties that we just derived. First of all, it has two properties, besides being, of course, computable in polynomial time. The first property is that the output is expanding, which means we can take as input a small string, in this case we call it a thls, and the PAG will make sure that the output will be longer. That's the expansion. The second property that we have is pseudorandomness, and it essentially means that the output of the PAG looks as being random. Formally, we express this again in a distinguishability game, which means either we give the adversary as input an output of the PAG, or we give the algorithm as input a random string, and it actually has to tell whether the output was computed via the PAG or via the random sampling. You can really think about it. You might wonder why. So you might wonder, why is the algorithm outputting 1? Well, this is just arbitrary. You can really think about it that the distinguisher says, oh yeah, I believe it's a PAG, and then I output 1. And therefore, the same number of times the algorithm is outputting 1 must be roughly the same number of times when it's outputting this 1 also received a random input. Right? So the probability of outputting 1 must be roughly the same in both cases. So now let's take a look at the concrete example. So we start by a PAG. At this point, we don't really care how it works. We just treat it abstractly. We start with this PAG that takes as input n bits, and it outputs an n plus 1 bit string, which means it expands its input by 1 bit. And to learn how to work with this definition and what the properties are, we usually like to choose these artificial examples that show us what the properties are and how to work with it. So let's take a look at the first example. This works as follows. We start with our PAG G, and we are appending a fixed bit 1 to it. And the result we are saying is the computation of a potential function G1. Is G1 a PAG? Yes or no? Well, the answer is no, it is not a PAG, because we essentially have a fixed bit B at the very ending, and this cannot be, right? So with probability 1/2, this bit should be either 0 or 1. So what about the second example? Intuitively, the second example tries to fix the bug from the first example by saying, okay, I cannot fix the bit B, so let's simply choose this bit B uniformly at random. So is this a PAG? Yes or no? The answer is no, it is not a PAG. And why? Well, because a PAG is a deterministic algorithm, there's no randomness involved, and therefore you cannot sample any random bit at this point. And therefore, this construction simply does not satisfy the properties of the PAG. So what about the third example? The idea is that we would like to increase the output even further, so why not simply concatenate the output of the... So let's take a look at the third example. The idea of the third example is to essentially just concatenate the output of the PAG. In other words, we simply execute it twice, and then we concatenate the output to each other. And the intuition might be that, well, the first part was uniformly random, and if I concatenate two random strings to each other, then the output should be random as well. Right? No. Why? Well, because we are concatenating the same string next to each other. In other words, we could build a simple distinguisher that says, if the first n+1 bits equal to the second n+1 bits, then I output 1. And the case that this happens for a uniformly random string is actually very small. And therefore, this resulting PAG is actually not a PAG. So now that we have learned what a PAG is and how to play around with it, let's build an actual encryption scheme out of it. And we're essentially following our basic idea, namely we are saying, well, I don't want to XOR the key directly because it might be too small. Instead, I will use the output of the PAG in order to derive an encryption scheme, and this is exactly what you can see here. The resulting encryption scheme is defined as follows. We have the three algorithms: the key generation algorithm, which essentially just chooses a seed S, an encryption scheme that takes as input the message and the seed S, which now, of course, corresponds to the key. And what it does is it runs the PAG on the seed and will XOR the output to the message. And this is the resulting ciphertext. And now to decrypt this message, obviously you're doing the reverse operation, which means you're taking as input the ciphertext C and the seed S. And what you will do is you will simply compute G of S and XOR the result to C. And what you will obtain is the message M that was encrypted, the plaintext M. So what about the security of the PAG? And in this case, we obtain the following theorem that says, if the PAG is secure, then the underlying encryption scheme is secure against an eavesdropper. And we will also take a look at the formal security proof shortly. So now that we've seen how the resulting construction looks like, the question is it actually secure? And we will take a look at a formal security proof and a formal reduction in the next video.